Alright, time for sample problems from 5.2. Let's start with number 1. The indefinite integral of 5 over x dx. So this one's pretty easy. We can look at it as 5 times 1 over x dx and take out that multiple of 5. Okay, and whether we look at it like this or we look at it like the book tends to reference it, dx over x, a function under its own derivative, the antiderivative of this would be the natural log of the absolute value of x. So 5 times the natural log of the absolute value of x. So that's just a matter of taking it a constant multiple and using the log rule for integration. When we have 1 over x plus 1 dx, well, we're going to get into U-substitution, but we don't really need to use U-substitution here. If we just notice that this is u, and this is du. If I took the derivative of x plus 1, it would just be dx, right? The plus 0. The derivative of 1 would be 0. So we have du over u, and we've already discussed how, by definition, this is the natural log of the absolute value of u, which is x plus 1. Number 8. Yeah, let's see, the indefinite integral of x squared over 3 minus x to the third. We got dx there. Okay. So now that we recognize that if we could make it look like this, du over u, we could just say natural log of u. So that maybe we'll take a few more steps. Maybe we need U-substitution to help us out. Keep everything straight. So what we want to do, if we're going to use the natural log rule, is to get this to be the function and this to be the derivative, right? Derivative over function. Function under its own derivative. And we can see that that's close. If we take the derivative of this, we'll get negative 3x squared, and this is x squared. Or maybe we don't need U-substitution. Maybe we just need to recognize that like this needs to be, let me get yellow here. This needs to be negative 3x squared. So if we put a negative 3 out there in front, then this, if this were u, that's kind of sloppy, but if that's u, now negative 3x squared dx, that's du. So we have du over u. So that's good. Only we put a multiple of negative 3 there, so we need to cancel that out. So it's like we didn't do anything. Because we can't just put a negative 3 multiplier in there, but we can cancel it out with a negative 1/3. So we get as negative 1/3 times the antiderivative of du over u, which is the natural log of the absolute value of u, and u is 3 minus x squared. Alright, so that's a pretty simple one. Didn't really have to pull out the u, like pull it over the side or anything. So, we didn't have to worry about that. But as they get more complicated, maybe we'll have to do that. So now we're on number 10. It's the definite integral, or the indefinite integral of x over the square root of 9 minus x squared dx. Okay, so now we're like in this habit of saying, let's make the bottom always be u, the function, and then have this be the derivative. Only if we let this whole thing with the square root and all be u, then we take the derivative of u and we wind up using the chain rule and stuff, and it's definitely not x dx or really anything close to that. So then we get at a loss as what to do. But the thing about this section, this chapter that I stated before, was we're expanding our ability to take antiderivatives, which doesn't mean throwing away all the old stuff we used to do. It means including it. So that's basically what's happening here, where we have an old kind of a function that we don't need the log rule for. All we need to do is let u be equal to, not the square root of 9 minus x squared, but just 9 minus x squared. And then we get du equals negative 2x dx. Okay, but we want to replace x dx. So whether we put a negative 2 over here or we change this so that one side of this is just x dx, let's do that over here. We'll get negative du over 2 equals x dx. Okay, so now we can replace x dx with negative du over 2, or negative 1/2 du. So now this indefinite integral becomes negative 1/2 du. Okay, so we'll put the negative 1/2 out here, du, over what? The square root of u. Okay, and this is not the log rule. This is simply the power rule. We have negative 1/2 times the integral of u to the 1/2 power du. And this is, like I said, it's just the power rule. So we have negative 1/2 times, now we add 1 to the power, that's u to the 3/2. And then we put here a multiple that when we multiply by 3/2, we don't get 3/2, we get instead a 1 here. So we put 2/3 and plus c. And then we fill in what u is. So we fill in this with what u was, so negative 1/2 times 2/3, so that's going to actually turn it into negative 1/3 because this 2 would cancel with this 2. So negative 1/3 times u, and u was 9 minus x squared. We're going to raise that to the 3/2 and add c. Okay, so the lesson here is it's not always as easy as using the log rule. Sometimes we don't need the log rule. We can go back to previous rules. And so this turned into just the power rule. So watch out for that. Okay, now number 11. So this is kind of a new idea that we're going to look at here, but we get this kind of a long thing. So now we have this seemingly crazy thing, but if we look at it, we just we'll notice that this function is 1 power higher, 1 degree higher than this one, and if we were to take the derivative of this, we would get an x squared, we'd get an x, we'd get a constant. So let's see what that would look like. U would be x to the 3rd plus 3x squared plus 9x, and du would be 3x squared plus 6x plus 9. But we see that, well, then times dx, of course. But we see that this is not 3x squared plus 6x plus 9. But if we were to multiply this by 3, we would get this. Or in other words, if we took this to be 3 times x squared plus 2x plus 3 dx, there we have it. We factored it out, and now this part is exactly the same as this. And so du is basically 3 times bigger than it needs to be, so whether we put a 3 here, which I'm going to choose to do this time, and then a 1/3, or if instead we choose to divide both sides of this by 3 so that du over 3 equals this original blue part, whatever, right? This is where being skilled at U-substitution comes in handy. So now this could be replaced with du, and now this becomes 1/3 times du over u, and that cleaned up a lot. Like, that becomes a much easier. And the indefinite integral of du over u would just be the natural log of u, and u is x to the 3rd plus 3x squared plus 9x. Alright, so it's just a matter of throwing a multiple in there. Alright, next we're going to move on to 15. And I misspoke before. I said 11 was going to be this new idea. 15 is actually that new idea. It's going to be a little bit of a challenge. So what we run into here is, if we were to consider this to be u, thinking that we would get du over u, when we take the derivative of this, we don't get x to the third. It's way off. We would need to just get like a dx up here. If I wanted x to the third to be the derivative, this would have to be x to the fourth. So what do? It only works to have a higher degree here than here. In fact, just 1 degree higher here than there. So what are we going to do about that? So if we actually do this division, then we'll get, if you remember long division of polynomials, we'll get this whole piece and then a remainder. Well, it turns out that remainder is going to be the part that we use the natural log rules on, the log rule for integration. So we got to do that long division. Okay, so we're going to take x to the third minus 3x squared plus 5. We're going to divide it by x minus 3. Alright, so we're trying to, like, this guy up here is going to be something we can multiply by x minus 3 to get this. So it's that first term that we would start to distribute into x minus 3 to first at least get x to the third. Well, we need an x squared. X squared times x would give us x to the third. Okay, but we're going to need more, because if we do x squared times negative 3, we'll get negative 3x squared, but then we don't get a 5 there, right? So what we do here is we subtract, find out what we're missing. So we subtract, we get 0, and then we find out there's still this 5 that we haven't made. Like, we haven't made this 5 right here. We don't have anything up here that we can multiply by x minus 3 and get the 5 that we need. So that's where we say remainder 5, right? There's 5 left over that we couldn't get. So that's what we call remainder 5. And what this really means is we have x squared plus 5 over the original x minus 3. Like, 5 was never part of the process of dividing by x minus 3, so it still needs to be divided by x minus 3. And the way you can look at it is x minus 3 times this. Well, we'll get x minus 3 times x squared, which will give us x cubed minus 3x squared, just like we want. And then we will multiply x minus 3 times 5 over x minus 3. The x minus 3 will cancel with the x minus 3 in the denominator, and we'll get the plus 5 that we needed. So this times this is x cubed minus 3x squared plus 5. So the reason we do this is we can rewrite this as the indefinite integral of x squared plus 5 over x minus 3. And we got the dx there. And now we have two separate integrals. We have this one, the indefinite integral of x squared dx. Easy. I can take the derivative of that, or the antiderivative, plus the antiderivative of 5 over x minus 3 dx. So this is just x to the third times 1/3. So that's good. If I take the derivative of that, I'll get x squared. This here, we should be in the habit of thinking that this is u. Okay. And the derivative of u would just be dx. It would just be 1, right? The derivative of x is 1. 1 times dx. So what we have here is 5 times 1 dx. So, like, if we put that, then that 1 dx would be du. And we'll just move this 5 out in front. Right? Take that constant multiple out. So we get plus 5. And now we have du over u, which uses the log rule. That's the natural log of u, which is x minus 3. So by doing long division and basically forcing this to be a whole, quote, whole piece, and a remainder, the remainder will always, always, pretty sure about that one, it'll be always the form of basically a function and 1 degree lower than that function. Okay, so then we split it up into two different indefinite integrals, and we can take the indefinite integral of each. All right, so consider that when you're looking at an integral. Maybe you should do long division if you notice that this guy here is a higher degree than this one, because if the log rule is going to work, we have to have, if this is degree 2, this is degree 1. If this is degree 3, this is degree 2. If this is degree 4, this is degree 3, and so on and so on. But if this is degree 1 and this is degree 3, that doesn't make any sense. I can't possibly write that as du over u. So it's just another tool, a weapon in the arsenal of our integration skills. Next we'll do 19. Indefinite integral of the natural log of x squared over x dx. Okay, so now we have the natural log of x in the integral. So that's kind of upsetting. But it's not too bad, because what we'll notice is this could be written as the natural log of x squared times 1 over x dx. Well, what do we have here? We have a function and its derivative. If we let this be u, just the natural log of x, not natural log of x squared, then this is du. And so what this becomes is u squared du, right? And then the antiderivative of that would just be 1/3 u to the third plus c, and it's just remains to replace u. U was the natural log of x. Natural log of x plus c. Okay. Let's see. And this should be raised to the third power. So if we took the derivative of this, we'd use chain rule. We get 3 times 1/3. That'd be 1, and then we subtract 1 from the power, so we have natural log of x squared times the derivative of the inside. The derivative of the natural log of x is 1 over x, and so there you go. You get your integrand back. So we didn't have to use U-substitution to turn it into log form, even though there was a natural log in there, which can be confusing. But that's all part of strengthening our overall abilities, is saying, I don't see this as needing the log rule. I see this as a function times its own derivative. So just something to consider there. Think about, do I need the log rule here to integrate? Sometimes yes, sometimes no. So that's what I'm trying to get across, is don't get too stuck on the log rule, but if it seems to jump out at you, then go for it. Like here, 1 over x times the natural log of x to the third dx. Okay. So first of all, we have this x to the third. I don't like that third power. That's a little bit troubling. But the properties of logs help me rewrite this as 1 over x times 3 times the natural log of x. Right? Because if we have the natural log of x to a power, we can take that power out in front. Now this is x times 3 times the natural log of x. So this could be rewritten as, well, 1 over, basically 1/3 times 1 over x natural log of x dx. So we could take that 1/3 out of the integral and get 1 over x times the natural log of x dx. So now what do we do? Well, see, we have a function in, or a natural log in the denominator. In this example, it was in the numerator. So what do we do about that? Well, if we try and separate it similarly to the way we just did, then we'll see we have 1/3 times the indefinite integral of 1 over the natural log of x times 1 over x dx. And this is the derivative of this, right? If this were u, then this would be du. So looking at it that way, we have du times 1 over u, or we have du over u. And what's the derivative of du over u? It's the natural log of the absolute value of u. 1/3 times the natural log of the absolute value of u. U was the natural log of x. So it's the natural log of the natural log of x. Alright. So I know it seems tricky. There's a lot of things coming at you. You just need to consider, can I write this in this new way, in the way of du over u? Alright. Just a little bit of a summary. So up to this chapter, we've had the antiderivative of u to the n du. That's where we add 1 to the power, and then we multiply by 1 over n plus 1 plus c. That worked as long as n was not -1, right? It could be -2, -5, it could be 1/2, it could be 6, it could be -2/3, it could be anything but -1. Okay, so this new chapter has introduced n to the -1, or 1 over n, 1 over u times du, or du over u, which is the natural log of the absolute value of u. Okay, so it's just one more form that we try and fit integrals into. We also have things like, if we could get the sign of a function times its own derivative, we could call that the negative cosine of that thing. If we had the integral of cosine of some function times its own derivative, then that would be the sine. Plus c. This should look like the negative. For secant squared, if we could get it to look like secant squared of a function times its own derivative using U-substitution, or just by kind of seeing it in our mind's eye, then we say that's the tangent of u plus c. And we have all these other rules that have to do with the antiderivative of secant tangent, secant of u times the tangent of u, the indefinite integral of now we've expanded to cosecant u du, and secant of u du, and tangent, just a single tangent, and cotangent. And we even have a couple left over that were just kind of obscure, which were, we could take the integral of the cosecant, no, let's see, what am I looking for here? The cosecant squared. Okay, a little bit obscure. That's the antiderivative of the negative cotangent. And then we could do, let's see, looking for that last one. Yeah, the definite integral of the cosecant u, cotangent u du. Well, that's just, negative cosecant u. So all we're trying to do is get our integrand to look something like any of these. These are probably more straightforward, really, because it makes it obvious that we probably wanted to get to look like sine of u du, if there's a sine in there somewhere. These two become a little more challenging. Is it u to the n du? Is it 1 over u du? And that just takes practice. Sometimes you're going to want to do long division of polynomials. Sometimes you're going to want to, what else? There's a natural log in there, and that just makes it more difficult. And I get you on that. It just takes practice. But we're going to practice a little more together here. 29, and we'll approach this in a couple different ways. First, using the log rule. So we got cosine of theta over the sine of theta times d theta. Well, here, if this is u, then this is du. And so we have du over u, and so we have the natural log of u, which is sine of theta. Okay, I said we were going to do it another way. This could also be written as the indefinite integral of cosine over sine is another way to define the cotangent. And now, if we look back on page 337, we have all these new antiderivatives, and this antiderivative is, no surprise, the natural log. The natural log of the sine. Of course, it would have to be, because we just did the work and proved it ourselves. Right. So whether we see it as du over u, or we just say, hey, there's this integral of cotangent on page 337 that I can use, either way. 32, another trig function involved here. So we have the definite integral of the secant of x over 2 dx. Okay, so again on page 337, we find that the definite integral of the indefinite integral of the secant of u du is equal to, we flip back there, it is the natural log of the absolute value of the secant of u plus tangent u plus c. Okay, we just don't quite have that. We have secant of x over 2, but this is not the derivative of x over 2. If this were u, this would not be du. So it's not secant u du. But we could make it secant u du if we consider what the derivative of this is. It would be 1/2. So if we put a 1/2 there, now this is du. Secant of u times du. The only thing we need to do is give that multiplier of 2, so we cancel out that 1/2. So this would be 2 times the antiderivative of secant of u du, which is the natural log of the absolute value of the secant of u, but u is x over 2, plus the tangent of u, which is x over 2, plus c. Alright, so it's just U-substitution, throwing trig functions there in the mix. Next, let's look at 38. So there is this function, and its derivative is given here. 2x over x squared minus 9. And it also says, it gives us 0, 4, and I'll remind you the significance of this when we're talking about differential equations. So there is a function, and its derivative is given by this function. So some function has this derivative. You know, I take the derivative of something, and I get 2x over x squared minus 9. So how do I go back and find f of x? That's what antiderivatives are, right? That's what indefinite integrals are. So if I take the antiderivative of 2x over x squared minus 9, I haven't forgotten about the 0, 4, I'll explain it here in a second, that will give me f of x, right? So to do this, we'll see that this is u, and this is du. Right? If this is u, then the derivative of u would be 2x dx, and we have 2x dx here. So you have du over u. So this is the natural log of the absolute value of u, which is x squared minus 9. What do we always put on the end of an antiderivative? Plus c. So that's where this comes in. This is a solution to this function. Right? They're saying that there's some function f of x, and that when you plug 0 into f of x, not this function, but the function that has this derivative, when you plug 0 into it, into this, we just found f of x, then you get 4. They're saying f of 0 is 4. That's what this means, right? You plug in 0, you get 4. So, what they're saying is the natural log of the absolute value of 4 squared minus 9 plus c should give, oh, I'm sorry, not 4 squared. I was supposed to put in 0, not 4. So let's back up. The natural log of 0 squared minus 9 plus c equals 4. And so we solve for c. And now what we have is the natural log of 9, right? Because the absolute value of negative 9. The natural log of 9 plus c equals 4. So c equals 4 minus the natural log of 9. And so this goes in the place of c. So in the end, f of x, that function we were looking for that has this derivative, specifically that has the point 0, 4 on it, or has a solution, is given by the natural log of the absolute value of x squared minus 9 plus 4 minus natural log of 9. That's the very specific solution, or what we call the particular solution. Specific or particular solution. So there we go. That's we were given a differential equation and a solution to that equation that has this derivative, and found the particular solution. Next, we're going to deal with some slope fields. Okay. Let's see. So we have this slope field. And sorry for this really crude drawing of that slope field, but there it kind of is, and you can reference your book to see a better picture of it. But let me explain again what a slope field is. We've taken the derivative of some function, that's what dy dx means, and we've gotten 1 plus 1 over x. So this is the derivative of some function, so this defines the slope of some function. So if we want to know the slope of this function, let's say we want to know the slope of this function at 1. So let's see. Yeah, at 1. So 1 plus 1 over 1 is the derivative at 1, and this would be 2. So we have a slope of 2 at the value 1. Okay, let's say we want to know the value of the slope of this function at 2. 1 plus 1 over 2, that's 3/2. Okay, so it's getting smaller. It's smaller than 2. And then if we want to know the value at 3, we'd be 1 plus 1 over 3, so we would be at 4/3. And so we're getting smaller, and we're getting smaller and smaller and smaller. And really what we're doing is we're adding, as x gets larger, we're going to add on a very small piece. Like if x is 50,000, we'll add 1 plus 1 over 50,000. And so that's not very big. It's really, really small. So it's going to get closer and closer to 1. So that's what we're seeing here. At 1, at x equals 1, we have a slope of 2, so it's rather steep. And then as we move over to 2, we have a slope of 3/2. And as we move over to 3, we have a slope of 4/3. And as we move further and further and further, we'll have a slope of close to 1. So you can see that's what's going on. These slopes don't look all that different because they're all just pretty close to 1 and getting closer. And that's all these slanted lines are. They represent the slantiness of the function that has this derivative. So there's tons of functions that could have these slopes. You could start drawing down here and have these slopes and just follow these slopes. Make sure that your function has this slopiness. But it goes through this point. So if we know it goes through this point, we just know it has this slopiness, and then it has this slopiness, and then it goes like almost vertical here as it approaches the y-axis, and then it has this much slopiness, and then that much, and so the actual function that has this derivative looks like this. So that's what we're supposed to do. We're supposed to sketch that. And then we're supposed to actually find the function that has this derivative. Well, if there's a function that has this derivative, we're going to find the antiderivative of this function. that's just how it works out. So now we can take the antiderivative of 1, and that's just going to be x. Right? The derivative of x is going to be 1, so that's good. And here we have the derivative of dx over x, which would be the natural log of x. So this is a function. If you took the derivative, you would get 1 plus 1 over x, and there you go. Plus c, of course. But remember, this is very similar to the previous problem. This function, f of x, okay, this function, f of x, has this derivative, okay, and this is telling me if I plug in 1, I get 4. So f of 1 equals 1 plus the natural log of 1 plus c, and that will give me 4. So then I just solve for c. So we get c is equal to 4 minus 1 minus the natural log of 1. Well, the natural log of 1, it's one of those properties of logs that is 0. So we just get 4 minus 1, or 3. Let's see, this is our family of functions, and then c is specifically 3 for this example. So our f of x is x plus the natural log of x plus 3. Because we found what c would have to be in order to plug in 1 and get 4. Alright. Let's see, do we have any more? We have 2 more. 48 and 49. It's just a matter of taking our skills and applying it to definite integrals. Okay, so we want to find the definite integral from -1 to 1 of 1 over x plus 2. So the fundamental theorem of calculus tells us that we can find the antiderivative of 1 over x plus 2 dx. Should have put a dx up here. Then we can take that antiderivative and plug in 1 and plug in -1 and subtract. So we just need to find that antiderivative. So this, if you'll notice, is u. This is du. So we have du over u, and we get to say that this is the natural log of the absolute value of u, which is x plus 2 plus c. Okay, then we can plug in 1, we can plug in -1 and subtract. So we have the natural log of the absolute value of 1 plus 2 minus the natural log of the absolute value of -1 plus 2. This is the natural log of 3. I don't even really need to put absolute value there. 3 is positive, so we don't need to take the absolute value. Minus the natural log of 1. 1. The natural log of 1 is 0. So we get the natural log of 3. And that's it. We don't really need to write a decimal. We can write natural log of 3. It's acceptable. It's the exact right answer. Okay, we're going to move on to 49. That'll be our last one. So the definite integral from 1 to e is that special number that we talked about before. Has special properties within the natural logs and elsewhere. Okay, over x dx. So we need to find the antiderivative. And then we'll use the fundamental theorem of calculus. Natural log of x, and we're squaring that over x dx. So, you know, our skills need to be strong. We need to be well practiced, and maybe practice more than what's assigned even till we get the hang of it. If you see the natural log of x in an integral, you're probably going to want to find somewhere in there 1 over x, right? Because that's the derivative of the natural log of x. And we like to have functions and the derivatives inside of integrals, right? We should get used to that idea. So if we rewrite it, we can have 1 plus the natural log of x squared times 1 over x dx. So now if we look at this, this could be u, which makes this whole thing u squared, right? And then this, if this is u and we take the derivative, we'll get 0 plus derivative of natural log of x is 1 over x dx. So this is du. So now what we have is u squared, Remember that squared is there. We have u raised to the second power du, and that's the simple power rule. That's just going to be u to the third. We're going to raise u to the third and multiply by 1/3, and that's it. The only thing here is we need to plug back what u is, right? U is 1 plus the natural log of x. I'm going to raise that to the third. Of course, we should be writing plus c here if we're going to be good math students. Then we're going to plug in e, we're going to plug in 1, we're going to subtract. That's the fundamental theorem of calculus. So here it is. There's the function we're going to use. We don't get mixed up here. 1/3 times 1 plus the natural log of e. We're going to raise that to the third power. Then we're going to subtract 1/3 times 1 plus the natural log of 1. And raise that to the third. What do we have here? The natural log of e is such a special number with the natural logs because the natural log of e is 1. And so we have 1 plus 1. So together we have 2. So here, this all together is 2 to the third. That's 8. Okay, so this is 8. 8 times a third, that's 8/3. Minus, okay, what do we have here? Natural log of 1, we even talked about it up here, it's one of those properties of natural logs. It is 0. So this just is 1. This is nothing. This is 1. 1 to the third is 1, so this is 1. And 1 times a third would just be 1/3. So this is 7/3. That'd be it. Alright, so thanks for watching. Thanks for hanging in there. Let me know how these videos are going. Contact me however you can. Let me know if you're having any issues, if you're having any confusion, and I'll try and help you out the best I can. So thanks for watching, and I hope that was helpful.